So good afternoon. As was introduced, my name's Adam from Arzon Solar. The title of my talk is CPV Lessons from the First 100 Megawatts and the Explosion of Next Generation Technologies. Actually, a slight edit. It's more like 200 megawatts these days, but let's just keep moving. So this is an outline. I'm going to skip over this for the interest of time. We're just going to get right into, for an introduction for those who might not know, what is CPV? CPV is very simple. It's a branch of photovoltaics where light is concentrated before it is converted by a photovoltaic device. It uses less semiconductor per watt than other types of solar. It also allows for use of very high efficiency multi-junction devices that are very expensive but can be used because it's far less material. Where modules are these days, you're getting a concentrator standard operating efficiencies around 31% of modules and also systems. If you're getting something less than this, then you should probably pick a different vendor. These do require dual axis tracking. So just to get right into kind of the facts of the industry, this is essentially the cumulative high concentration photovoltaic installations to date. So we're just about at 200 megawatts with about eyes on 250 megawatts by the end of the year. On an annual rate, this is how that looks. And essentially, 2014 is expected to be the first year where high concentration photovoltaics will install at 100 megawatts. This is due primarily with help from a few very large installations, and it's actually, all of the numbers I just showed you are from only 3 companies. So the biggest installation of HCPV right now is a Suncor plant in western China. The next biggest is a Soitec plant, which is essentially finishing installation at this moment in South Africa. And then since 2012, we've had a plant running, formerly of Amonix plant, Amonix Technology in Alamosa, Colorado. So one critical question with CPV is kind of where does it go? Where does it work? Everyone kind of knows that it's supposed to work in very sunny areas, but what does that mean? So most concentrators will work well at a DNI of 5 or 5.5 daily sum average and above. And the higher you go in DNI, the more competitive CPV is going to be. So that's essentially all these areas. So I would submit, while it's not circling the whole globe, that it's still a lot of area. It's a lot of very sunny places on this planet. And a lot of them are newer, growing population centers, like MENA, US Southwest, South America, China. So a little bit about Arzon Solar. That's probably a new name for most people. Arzon was formed to acquire the assets of Amonix in June of 2014. Our headquarters are in Seal Beach. Our CEO is Vahan. Our CFO is Bob. And I'm the technical guy. Nice to meet you. So the company is committed to the design and manufacturing of high-performance photovoltaic generation products using the technology and expertise developed from the years of operation and experience with Amonix. Many people have heard of Amonix. Amonix raised a huge amount of money, built a lot of product, and then kind of disappeared. Arzon is the step 2. Amonix was founded in 1989, so it was one of the longest living concentrator companies. And the 7700 product was the one that commercialized the most, with 50 megawatts installed from 2010 till 2012. And the latest product is the 8700. And this is the 8700. This is, just to give you kind of some facts and figures about this product, this is a utility scale generator. It's a 30% lower cost than the previous product. So that's the cost to us to build it, is 30% lower. It's 10% higher power performance. So the power coming out of this is 10% higher than its previous generation. So this gives it a CSOC, which is like a PVUSA rating of about 70 kilowatts DC. The CSTC rating is 84 kilowatts DC. Now the beautiful thing about a concentrator is they're incredibly high energy generation. So this is a 2400 to 2700 watt or kilowatt hour per kilowatt generator, and I'll explain more about that number. This translates directly into incredibly efficient land usage. So in the most recent NREL land use report from June 2013, concentrators were the most efficient use of land when you consider acres per gigawatt hour per year. So I wanted to take a moment with the audience to explain one of the big failures of CPV in the past, which is how to compare cost of CPV with cost of other photovoltaic generation. The point being, CPV cannot be fairly compared on a pure dollar per watt basis. So that's, if you take nothing else away from this talk, please take that fact away. You need to make adjustments. With modules, you need to remember that CPV only uses the direct portion of sunlight, which is 85 to 90% of the global. CPV is less sensitive also to temperature-induced efficiency loss to silicon. With CPV systems, you must consider that you're going to need to pay for a dual-axis tracker because this is an optical system. So I just want to do a quick example using some market data that I hope helps people to understand how to compare costs in CPV. So this is a chart that was published just a few months ago from Green Tech Media on the costs, the installed prices of projects in residential, commercial, and utility. And if you just take a normal PV panel, so I picked an Astronergy 240 watt DC STC panel, right off the data sheet, you can find out that the PTC value, the PV USA value, is 218 watts. Now, if you just take the $1.85, which is the price, you can figure out what the corresponding operational PV USA price of this plant is. It's $2.01 per watt. Now, if you take the Arzon Solar 8700, this is a 76.3 DC STC generator. You can see I've already made an adjustment, the 900 watts per meter squared, because we only use the direct portion. Now, if you get the PV USA or the PTC value, that's 70.5. But the thing you have to remember, and the thing that I skipped over with the Astronergy panel, is that if you have a fixed tilt system in Las Vegas, it's 1,970 kilowatt hours per kilowatt. So that's the amount of energy you're getting per kilowatt of your system. That is a PV sys number. So this is no funny business, this is just an industry tool. If you use the same PV sys tool, it's 2,720 kilowatt hours per kilowatt, dual axis in Las Vegas. So that allows you to do some very quick, what we call energy adjusted math. You take the 201, you do essentially an energy ratio times the power of the Arzon product, and you get the cost that you would have to pay, or that Arzon would have to charge essentially per system to be competitive at today's prices. If you convert this back to dollars per watt PTC, it's $2.80 a watt. So if I come to you and say our solution's $2.80 a watt, and you say, well, everyone else is $1.85, we're talking about the same number, essentially. So this is very important to remember that the energy generation of CPV is that much higher. Okay. So one of the things we wanted to talk about with this talk was the lessons from the 200 megawatts installed thus far. First, CPV is a global business with global opportunities and therefore must be logistically flexible. I think there's no better example of this than the 3 largest projects in CPV are on 3 different continents. Second, the product performance is mature. And then a subset of that, dual axis trackers are way, way better than they were 5 years ago. I've been in CPV for 7 years, and I tell you some of the tracker technology now is far better and is also far less expensive. Modules are showing very stable performance in a whole host of conditions. Third, this is more of a failure. The value of CPV message has been poorly communicated in the past. I believe clear communication is completely necessary so that we do not miss future opportunities. Last, a CPV business relying on utility scale solar alone or utility scale customers alone is not stable. It's very much like a construction business where you're either feasting on a giant project or you're in the famine looking for projects to do. So let's talk a little bit about competitive advantages of CPV. First is, or the old reason for CPV was essentially, well, we use a lot less of that semiconductor, and that stuff is expensive. We all know that. Well, that has changed. So the new reason is essentially CPV is a superior performance, superior efficiency, superior energy density. And it's really just, if you look at classes of performance in photovoltaics, it's a high-performance device. The best way to kind of show this is to just look at data from our biggest experience with CPV, which is the 30-megawatt AC PTC plant in Alamosa, Colorado. The customer was Cogentrix. This was 504 of our Amonix 7700 systems. And the actual data energy rating of this plant is 2590 kilowatt hours per kilowatt. This has been in operation since March 1st, 2012. So this is the full set of operation data from this plant. This is the output at the plant of the data for over 800 days. And I think the one thing that's really telling about what you should be expecting as a CPV customer is that if you actually look at the calculated degradation rate, it's 0.5% per year. So this is right where we expected it to be. I talked a little bit about the energy density difference. This is just a chart to really show visually what I'm talking about. As you move from fixed tilt to one-axis horizontal to dual-axis or CPV tracking, you really do get these steps in energy density. And our real point is, if you're going to put in power, why not get the most out of it with energy? Because that's where you're making your money. Oh, by the way, these are all values calculated with PVSys and then verified with real testing data. Okay, so the competitive advantage of CPV really is there's a few of them. One is efficiency. There's just no doubting the fact that if you take a CPV module today, it's roughly twice the operational efficiency of crystalline silicon modules. That translates directly into energy density, which if you look, this is data directly from the independent NREL land use requirements for solar power plants in the US report. This was published June 2013. It's available for free on the internet. And you look at the generation weighted average land use in direct area, you'll see that CPV is the lowest, which is good in this case, and it's the same thing with total area for the PV technologies. Okay, so I kind of blew through that because I really wanted to focus on the next generation stuff. And I think this is something that, as an attendee to the conference, you can really take advantage of by visiting the conference on concentrators, which starts tomorrow. So first thing is, on the next generation technologies list, is 4 and 5 junction cells. So like shaving razors, cells get better when you add more junctions. You just keep putting them on. But all of the cells being used today are 3-junction cells in commercial operation. Most of the cells are germanium-based bottom layer, and they have a usage breakdown of the spectrum that's essentially this right here, this graphic. Now, in an attempt to capture more of the gray, more of the difference between what's being captured and what's being left on the table, the experts in cells have been trying all kinds of things. First are 4 and 5 junction wafer bonded cells. Spectral Lab has announced a 5-junction wafer bonded cell. They announced that last year. They're working on that for space, one-sun applications, and they're seeing really great results. Soitec has already developed a 4-junction wafer bonded cell and tested that at 319x, and already have a spot on the best efficiencies chart. And then just recently in July, Fraunhofer measured a Soitec module which had those cells inside of it. So you're already seeing people tinkering with modules using these more exotic cells. And this will continue. There's nothing fundamentally stopping the number of junctions you can try to put on. The question is, how can you effectively use those junctions to benefit on an energy generation or performance benefit over time? The next one, which is most appropriate for SPIE, is spectrum splitting. So with these cells, all of the spectrum, all the binning of the spectrum happens in the semiconductor. There's a body of research out there right now that suggests maybe that's not the best way to do it. Maybe the best way to do it is to do it with optics. Split the light with optics, forward it to cells that are tuned specifically for that light, and that way you can achieve a better overall efficiency. If you come to the conference that starts tomorrow on concentrators, at least on the CPV portion, it's also a CSP session, but CPV, there's a lot of talk on spectrum splitters. I think some of the leading research in this is from Atwater's group at Caltech and from Kostuk's group in Arizona, University of Arizona, on spectrum splitting. There has been renewed interest from DOE, from the government, in supporting these types of approaches because of their ability to perhaps leapfrog existing generation. These are also seen as critical in combined heat and PV research. So that's where you're making electricity and you're also making electrical energy. Okay. The next thing, also optical related, is essentially just the engineering part. Optics manufacturing. I would say that other than overhead projectors, projection TVs, there hasn't been a huge market for Fresnel lenses. So when you start thinking about using Fresnel lenses in concentrators, you actually open up a whole lot of opportunities for improvement just on the engineering manufacturing processes side. So what I'm doing here is listing, there's two different ways to make lenses that are most popular. There's PMMA and there's silicone on glass. And each one of these has a whole list of things that could be better. Each one of these items here is an area for loss. It's also a big area for improvement. The next is loss reduction. So this is kind of in the same category, but it's actually just being a lot more intelligent about how you're actually concentrating the light. So every time that light interacts with an optic in a CPV system, you're opening yourself up for a loss. Finding intelligent ways to reduce these losses is kind of the fun of the game when it comes to this category. So we had been working on this for several years at Amonix, and we're able to achieve, using this methodology, able to achieve a 35.9% CSTC efficiency rating at NREL, which today is still the highest PV module that's ever been tested at NREL outdoors. So these techniques for just very carefully understanding your losses and what you can do to mitigate them do work. Next, another big topic for this conference is non-imaging optics. So there's been no shortage of people leveraging non-imaging optics principles into CPV. And this chart just kind of overviews why would you want to do that. Well, CPV, you essentially want to take this much sunlight and you want to get it onto this much cell, and you want it to be as uniform as possible. So if you use just a very traditional, what I would call reflective cone optic, you see what you get. You get hot spots. This is acting almost like an imaging optic. What you really want is something like this, which is a very even spread of flux over the entire cell surface, because this leads directly to better IV curves, better fill factors. So you're really seeing a benefit to performance here. If you move it off track, this is a tracking angle of basically pointing right at the sun. If you move it off track, the best non-imaging optics will compensate for that. So you can see that this non-imaging optic here, which is an LPI optic, essentially doesn't change when you move it off track, whereas some of these other optics generate hot spots or just start looking really ugly. Okay, so in closing, just a few final points. CPV products have matured quite a bit in the last decade. I've been in CPV since 2007, and it's really been amazing to see it kind of go through this kind of huge peak of interest and then kind of a huge detriment of interest, but then still have a very kind of even foundation of companies working and putting out product and installing product. I would say that real-world data overwhelmingly shows stable, predictable performance with over 200 megawatts installed globally. Performance and efficiency will continue to improve. This is one of the great things about CPV is there is no kind of fundamental limit that we're near in the performance of the cells, and to a certain extent even the performance of the optics. And I would say that CPV today is a competitive choice in high DNI environments and also high temperature environments, especially when performance and energy density matters. And I think since I have 30 seconds here, a little final story is I was sitting at my desk just the other day and I got a call from a guy in West Texas who knows a guy who owns a golf course. And the guy has a couple acres of land and he's subject to, I guess, like the power company shutting off power. He's losing customers. He's really very upset with it. But anyways, because of the area of land he has is very small that he wants to put solar on. He wants to get as much energy as possible. And so he's begging us to put a CPV system there. So I do think there is a market for high energy density and high performance. So with that, I'd like to thank you for your attention.